Josh Weitz, who's now a full professor at Georgia Tech. Did other things. Okay, so, all right. We're good with that? So I'm going to move into this fundamentals business. And it's going to have a couple of pieces in here, but we're going to start. We'll talk about data. I know some of these plots are getting older. The measuring, this references. Anyone? You don't have to. This is just me enjoying having fun. That tarot card, what is the reference for that? Yes, very good. The first of 3 Indiana Jones movies that exist. Okay, so we've gone, and this is what I like to say, we've gone from the data poor to the data poor to the data pouring is the hilarious joke there, but it's not bad. So data scarce to data rich, right? All these transitions are happening, and you're in the middle of it. So go and find a field that is taking off like that, and go and have some fun in it, basically. This is from a few years ago, but it still gives a sense of what's going on, right? So available storage is going like this: information created, information, which of course is just cat pictures largely, and videos, which is justifiable. But exponential growth, it's taking off. I should see if I can find a new thing for this one. This was 2013. We were getting to zettabytes, right? And after that, we get to yottabytes. I think it is. Let's look up yottabytes. I think I have that here. Yes. The yottabyte is 2 to the 80 bytes. I mean, it's really a lot of stuff, right? Petabytes is something that that's often talked about. Exabytes are next, zettabytes, yottabytes. Terabytes, that was monster bytes, right? That was terror is monster, so it was like, that's going to be the biggest one. This is but I think there's a trend here. We need some more things like that. We do end up with, at some point, you've got the number of quarks in the universe or something. So there's got to be a limit to all this madness. Sorry about that. Yep. And of course, it goes the other way, right? So these are big things. Yes. Yeah. Okay. So these are old now, of course, but Facebook, just an unbelievable number of photos and videos. And there's a big transition in them getting video to work, for good or bad, and Twitter as well, similar kind of thing. And Instagram changed to a stronger video thing, right? You can upload longer videos, and sadly, it is probably Facebook is going to completely own that one now. So, all right, data is taking off in all these places. This is just, and I'll give you lots of examples. This is one which was this is just a mark, I guess, what was a big transition in terms of literature. It was a pretty famous paper, but it's only 2011. It's only a few years ago. Google Books project, right? So Google munched up all these books, as they want to do, and scanned them all and then did image processing on them, which is not perfect, but if you've ever, these things kind of died out, I suppose, a little bit, but captures, right? So maybe you're too young for this, but right, you get this funny looking word with lines through it or whatever, and you had to type it in, and computers couldn't do it. Right? And then at some point, you started to get 2 of them. You ever see that? You get 2, right? And if you got 2, one was made by a computer as a test, and the other one was taken from a text, for which we didn't have a good guess for what it was. It didn't go through optical character recognition very well. So that was a survey, right? So you might ask 100 people what they think this symbol is or this word is, and that helped with filling in all the details. It's still true that if you go back to the early 1800s for the Google Books data set, that you see F's and S's are all messed up, right? S's would, so I guess F's looked more like S's. They were sort of more like this with a line in them. So there's some complications. It's not perfect, but roughly from 1800, it's pretty good. Lots of things came out of this first paper. So the way it's structured is for every year, you just have this massive set of books, but they've all been chopped up into 1 word, 2 word, 3 word, 4 word, 5 word, and that's it, right? So and you have counts for those, and you have the number of books those pieces appeared in, they're called n-grams, right? So 1 grams, 2 grams, 3 grams, 4 grams, 5 grams. There's an m-gram viewer that you can play around with, which was, kind of an exciting thing at the time. It's very helpful. Let's get it to work. Whoops. Have I lost my little? Come on. That didn't work, did it? Okay, that's the wrong one. N-grams. Right, so this has been sitting here for a long time. This is just comparing different things. So this is smoothing of 3. So these are these are 2 grams. So an n-gram is n entities together. Could be numbers as well, other things. Right, Sherlock Holmes help. So they did a pretty good job with this. But I have to say, coming out of this course, we had a student work on this very hard, and we thought we were going to do all sorts of amazing things like they had done in terms of finding out these long cultural trends, right? I mean, this was this great window into history that, looking around, there wasn't a data set at the time. And we'd use State of the Union speeches as something for the US, which gave us a couple of hundred years. Again, a sort of a thin view, but it was long. It turns out there's really a fundamental problem with this, which is that each book is only in there once, right? So and it's hard to avoid this, but you need much more metadata, right? Each book, so Harry Potter books, if they're scanned, they're in there once. And if they have new editions, maybe they're in there again. But books that no one's ever read, also once, right? So that's a weird thing. So this is like going to a forest and saying, I want to understand this forest, but you just have one of each species in front of you. And you weigh them, and you find the average amount of fur on them and stuff like that, and you do all these things and say, this is what the forest is like. But if it's a forest full of squirrels, then, and nothing else, then with just a few other random species, you've completely, made a mess of everything. So that's a problem with corpora in general. It's sometimes hard to overcome that. But the other thing is science was clearly fed into this, and medicine. So if you look at words like experiment, they took off through the 1900s, and it gave the illusion of this rather beautiful result, which is here. So this is fantastic. This is just the numbers, 1883, 1910, 1950, just how much they are present in books, normalized by frequency, right? So so there are peaks in 1883. The number 1883, of course, is going to be page numbers. You're just scanning it like a maniac, right? Or your computer's a maniac. It's scanning away. It's just going to chomp them all up and put them all in. But this is when 1883 is talked about a lot. And then there's this long, slow decay from that, right? And then there's a higher spike here, right? And this is not just this is normalized, so this isn't a volume effect. There's a higher spike here, and then a higher spike again. But it's also decaying a little faster. So there was this things are speeding up, which I think is true, but this was kind of gave you a sense that this was about stories and literature and our sense of the world, but it's really about science, because what happened was they just have a ton of scientific documents in this thing. It's not just books. So the framing misleads you, I think. There is a fiction section, and in the second version, the fiction section is pretty good. It seems to be just fiction. But it's a weird thing to look through because it's still a mixture of fiction and literary criticism. So you can sort of see words of similar coming from. But you see, for example, if you look far enough down, you see all these Star Trek words are in there. Picard and The Next Generation and so on, because there are a ton of books from those, and each one counts. Yes?
So in the data from Google,
yeah.
has basically one example of every book. That's kind of like a measure of species richness. You've got an example of one species, and there might be n number of species. But if you had some data on each of those books' popularity from somewhere else,
right,
you could merge them and get more of like a Shannon's diversity, which includes
right.
species richness
right.
and the number of each species.
Right. So if all of us and also like how many books we read, right? So if we all just read one book, we've got this big library here, but we all read what am I going to say? The Twilight books. Like, let's say we just read those. Everyone reads them. That's the thing that's in people's heads, right? Yeah. In that case, for worse, right? But, Buffy the Vampire Slayer. Anyway, so, but if we're reading them and you have like library records, right? For example, or whatever, or you have Kindle, you have, where people read. then you have a potentially a better way of saying that, right? And music that people listen to. It's hard to get that data. And the problem is at this point, you can't fix it up because all of these books have been, truly, at least digitally shredded and put into each year just has all the books that were published in that year. So we can't go in and find that this word was in this book. You can't undo it. Now, we do have this other data set, HathiTrust data set, where we actually have the books. And we have a student working on that. And if you're interested in that, we can work on that. But that's a gigantic set of books. And, right. And so it's the precursor to this. So that's interesting. But again, hard to sort out because things aren't tagged super well. Like you have to be able to say, this is a fiction book, or these are thrillers, these are whatever, right? I mean, these are really interesting things. I mean, one of the dominant fiction books that people read over time. There's a suggestion that after the First World War, it's more things like Agatha Christie and those kinds of mysteries, which had a nice, there wasn't much gore, but there was a mystery, and then there was an end, and it will be solved and sorted out, and that had a sense. There's a sense that that's not a good place to be in relative to the horrors of what was the Great War at that time. And I don't know if you can get that out with some of this. So we've been able to look at, there are some things that work out. Anyway, Eitan did some really nice stuff with this and a lot of hard work. But I think it's such a fantastically interesting window that's opened up. And of course, this is just within the last decade. So this will get better. And as I said, there are other things like HathiTrust that allow us to get at history. All right. And I know this is sort of one slide there. So we're going to talk about data, and then I'll have a piece that I just want to say about measurement of overall, how to quantify systems. So this is Lord Kelvin, may have said these things, right? I mean, I guess so. To measure is to know, and if you can't measure, you can't improve it, right? So this is these are good things, and we can forget this a little bit depending on the field you're in. You can get a little too excited about theory or whatever it is, and forget the big picture. But I've come to appreciate in some of the work we've done, and many other people have done, that we're building, instruments like you might build microscopes, right? And I'll have some more about that. But we're building the instruments you need in this big data world to kind of measure things. He also said some other things. So X-rays will prove to be a hoax. So we always cherry pick these things. There's nothing new to be discovered in physics. All that remains is more and more precise measurement. So quantum would have been a bit of a shock there. And then chaos theory, just a total disaster. Anyway, usually when people say these sorts of things, they're like very important people say these kinds of things, like we'll never get da-da-da. There, it's not right. Okay, so, and this is like a measurement instrument piece here. So just looking back over time, how we've measured time. So early on, we kind of got hold of the whole season thing, right? And started to realize that that it was pretty stable, and so we were able to put up some big rocks and time things and count things and so on, and things like Stonehenge and so on. So that was possible. Sundials are old, not super old in a way, but they seem to be maybe back here, 1500. But we didn't have anything much better than sundials for a long time, right? And now it's sort of insane where we are now. But these sorts of objects that we were able to, so hourglasses are, you've actually got to make something pretty well, I suppose, for that to work, but that took a long time to get to. Pendulum clocks of the 1500s. And then we get to this point, this is a very important point in history for measurement of time, was actually comes out of measuring longitude. Yeah, so some of you may know about this. So longitude was the very difficult piece to measure. If you're sailing around the water, being English and ridiculous, and doing bad things to the world, but and then crashing in. But occasionally you get destroyed, right? And that was a expensive bad thing to happen. And it was largely because they didn't know where they were in this direction, right? So their X bit was off. Latitude you could do with stars, right? That was good. They had the Polaris business. Not so good on the southern hemisphere, but it was workable. There was a couple of threads of how to do this, and a lot of money was offered at the time. It was, I think, really a large sum to solve this problem, right? So how are we going to measure longitude? And various directions were going off with with stars, right? We're going to have these elaborate maps and astrolabes, and we're going to do it. But you need to have all sorts of detailed records, these books to look up. But there was Harrison, and then his son were these sort of further. They weren't really in the the sort of inner sanctum of all of this. They were bent on building really, really, really good clocks that would, they weren't pendulum clocks. They were these mechanical things that would just tick. Yeah, and you could wind them up, and they would work for months and months. Potentially, because you need them to work for a year. You've been off wandering around in the water, and you're not sure where you are anymore. So. And then you could know what time it was back in Greenwich, and be able to figure things out from the day, from sunrise and so on. So this was a tremendous transition. But this is the 1700s, right? So now we can measure time well, and that begins to fit in with everything else we're doing with mechanical stuff, right? This is around the time where we begin to think maybe the world or the universe runs like this, and then someone says, well, what about God? And so that was a little bit terrifying for a few people. Galileo had sort of had his run in as well, but still it turns. I guess it's a little. I mean, he totally squibbed on it, right? He said, you guys are right. Anyway, so okay, so that's a big change. And then actually, Lord Kelvin, when you had this idea of atoms, I guess he said, we'll get to billionths of a second. So that was well done by him. This you don't have to read this, but this is, and I don't know if this is holding up super well, but it's true, at least in general, right? So the thermometers took us a long time to get to temperature, right? So we're very used to temperature. We have our own feeling for it, but the idea that you could measure it and that it would be something that you could make this instrument, someone else, you could give them instructions, they'd make an instrument, and do this in this nice scientific way was not really clear, right? So I guess there's some argument now about how much of this is really holding up. But the idea that people, of course, would have their own versions of temperature. It's not just, this is obviously some of this about humidity and so on. Yes, we could agree it's warmer today than it was yesterday, like it's a big change, but like how you feel, like there was a sort of a human element to it that might render it sort of impossible to be on a scale, right? Not like measuring distance. I'm going to make a stick, you can make another stick, and we'll mark it and so on. And we both have the same measuring sticks. And as it was for kilograms or for weight, and only recently this has changed, right? The kilogram for all of humanity was just this block of metal in Paris. That's the reference kilogram. Really just a dangerous kind of way to run science. And other things like seconds and so on, it's just a specification. So you have to go and find I can't remember the details, cesium atoms, I think it is, right? The decay and so on, and measure it from that. And that's a reliable thing that we have nothing to do with, right? We didn't make some object from which you have to all, make a reference. Nature did it. So this was something that took a couple of hundred years from there to build one. And again, I hope this sort of holds up. But there is this very interesting book, Inventing Temperature, that I have actually, just on the history of getting to making thermometers. And then you get into the 1700s, 1800s. Eventually, we have these really good ones, and then thermodynamics takes off, right? So all of this is to say you have to measure things well. Again, this may not seem surprising, but it's as we sort of move off into these sort of weirder realms, especially sort of social phenomena and human phenomena. Like, how do you measure them well? How do you actually come up with instruments that are reliable? More things about data. So this is sort of the summary of thinking, I suppose. So this is the pure math world, right? It's just you oscillate between these two states, and but this is unfortunately what happens, right? So and we were up until the 90s in a lot of areas. You were just like happily living up here, making up stuff, and then this happened. So, but it happened for physics, right? It happened for biology, right? Now there's DNA, and you can't make up things about humors or something or whatever. We observed enough rotations of planets and so on to figure out the ellipse thing and not get killed by religious people. And then you're back to sad. But anyway, you can choose your own path, right? But you can live here. That's okay. String theory people live here. Yeah. Mostly. Anyway, that's a very enjoyable feature of what's happened. Sorry, it's just ridiculous. I can't believe I did this. So bad.
Enough! You are all of you beneath me.
Sorry,
God,
out of control.
Creature, and I will not be bullied by that.
Puny God.
Very enjoyable. Okay, so I know it's a shame he's not there anymore. Anyway, spoiled. So yeah, the point being, data really is painful to look at. So if you're really happy about it, you should not look at data. You should not do it. If you love your theory, do not. Just yeah, because you'll be really sad. So you should start with data. All right, that's where we are now. So the charms of the many wrong paths, that's true. So this is again, no? Anyone? Third one, yeah. He chose wisely. Sorry. Yeah, so this is another important framing here for me, which is the knowledge of dead monks, right? So this is Newton's apparently, I need to look this up probably. Apparently he had sort of all sorts of ideas for what the law of gravity might be structured like, right? In terms of, where if it should be out of the fourth on the bottom and so on, and R squared seems kind of evident in some ways. So, but in science we do a terrible job of this, right? We do not have journals, which would be almost all of our journals, that will be filled with the things we did wrong, right? Here are the ways that I set the lab on fire. That would be a good journal, how to blow things that blew up. So we tend to kind of not talk about that. And there's a lot of after the fact, like my hypothesis is, and of course it wasn't, it's like, this is the 41st thing that you thought of. But we got ourselves into a bit of trouble. Yeah, so you shouldn't go into these places, right? Paths of thinking that lead to certain despair. It would be good to have a list of those things. Wikipedia. In terms of where we can eventually get to, and I think we've got a reasonable handle on this, unless we invent faster than light stuff beyond stories, because we have that, there's just an extent to what we can see, right? There's just the beginning of the universe, and then that light's coming to us, and that's as far as we can go. It's pretty good. What's this, 10 to the 30? This is 10 to the 30 here, minus 30 here, so it's 60 orders of magnitude in length scale. So this is big. So maybe this is true, right? So if you DC Comics, you're allowed to have interdimensional movement, which is insane. Great for stories, right? You just make up other worlds that are like yours. And we don't know about this business, right? I mean, we can make all sorts of hypotheses about this, but and they have to, of course, the very tricky part, right? They have to give rise to what we see macroscopically. So there is a real test here at least, but we're never going to go down here and find our strings, right? As far as we understand. It could be that one day we show that, here's the category of micro things that could give rise to what we see here. And that's it. We've got this whole box. That would be impressive, right? But I don't know. I don't know if we can do that. We'll see that. Anyway, so we're in about, 10 to the minus, in terms of measurable things, this is 10 to the minus 13, 10 to the 28. So that's 41 orders of magnitude. So that's a good field of play, shall we say. All right, limits of testability. This is just to say, just even the word scientist is a relatively new thing, right? This is different to Google. Oh, it is Google Books, yes. There's also trends, but this is, again, so this is not normalized in any way by popularity, but it gives you a sense. What Google Books does allow you to still do is like, does a word exist, right? When does it come in, So that's helpful. So in terms of like exploring the lexicon as that it's changed, there's some justification there for using it still. Anyway, so these are where these other ones are floating along. Seems to have dropped off, doesn't it? Anyway, disappointing. Anyway, scientists, yes. It's kind of funny. Okay, so this is just a little bit more about measurement. And I've been thinking about this for a while, I suppose, but we have this proclivity towards giving a system a one number, and you see this a lot. And it's great because then you can go and tell the policymakers or whatever the number went up or the number went down. This is apparently a real sign, right? This is a real sign. And it's a joke, but it's a real sign in this town. But yeah, right. So there's the Burlington presumably has, yes, right? Every city will have its own number, and this will be its score, right? So then you can compare them. But we, and that seems ridiculous, right? But obviously these aren't commensurate things in terms of there are feet and numbers and years being added together, so that's wrong. You need a conversion factor, sure, you've got some prefactors, you do the right thing. So well done there, whoever put that up, that was funny. So comparisons and rankings are easy, right? So it'd be great if we could do this. And so it's very hard so once you get in there, it's hard to push back against, right? So grade point average, right? Everything you do, one number. And when I went through high school in Australia, it was just one number at the end. It was just the top 4 out of 100 plus 10% of the fifth one. And that was it. That was your number. It was just a straight up ranking. And when you went to university, you listed the places you wanted to be or the fields you wanted to be in, and it just went down. All the other people who listed it just took the top one, and then just numbers, straight up numbers. So that one, which you're very familiar with, one of our students here who did a master's with us, and partly he did a master's with us because he had to get something that said A's and B's on it because he went to Evergreen State College, is that what it's called? Evergreen in Washington. It's where Matt Groening went. And I don't know how to say this probably. It's a giant clam, a geoduck, what is it called? Geoduck or something? That's their mascot. I think 10% of the population, the student population, live in the forest. It's like interesting place. Anyway, you would come out of there with like a 100, 400-page document of who you are. No A's or B's, nothing like that. It's just all this text. And which is awesome. But, then someone else says, I go to GRE or whatever, and all the systems are set up to do that. I mean, look, in the end, depends where you go, but of course, letters and recommendations, those things are absolutely gigantically important. Absolutely. So, there's a limit to how much people pay attention to these things. But college rankings, right? Of course, we have this thing, which makes colleges do bad things, right? What is it? The U.S. News and, got to be on that one. We had a project in here, and it could be done, which is measuring looking at all the tweets coming out of a college region, and then comparing all the colleges based on what people talk about and the happiness and so on. And could be interesting. Could be also kind of damning. How serious is this place? Whatever. The parents would have a tough time looking at that one, I guess. City rankings, we do this sort of thing. Countries, we rank them. The Michelin Guide, I mean, this is a 1, 2, or 3 stars. That's it. No in-betweens, right? And this is, and it's awful to say, but I mean, this is incredibly stressful what happens to people, right? There are chefs, awful thing to say, but have committed suicide, and it seems directly tied, right, to this, where it's gone, Michelin Guide put them down from 3 to 2. And maybe that's not right, but I think it's sort of Yelp scores. Again, just a 5-point sort of thing. Zagat. Does anyone even know Zagat? Zagat was the thing. It was Tim Zagat and his wife. I think just started to make this little thing in New York City years and years ago, and it became a book you would buy, right? Because before the internet, or before the web, I should say. And that always had 3 things to it, right? So it had some complexity to it, which was like the food, the decor, and the cost, right? There was some sort of sense of it being, maybe service, I think it was. So that actually had some complexity to it, but Yelp is just a thing, pretty much. And then, of course, you look at what people say. Amazon ratings. Amazon ratings have a peculiar thing. Let me look at this one. I have a nice one here for you. Well, let's find this one. Get open somewhere else. banana, yes, the Hutzler 5.7 banana slicer, which sometimes I use as a pointing thing because look, you purchased this on April. So, and oh my God, we've run out of time. Let me just tell you about this. Oh my God, I'm sorry, I monologued. I will tell you quickly about this. I was showing this to this class a number of years ago, probably 2013, because it was where the whole system had been gamed at that point, and it doesn't happen anymore, I think. Let's look at what. These are sponsored, who bought this. Also. See, look, it's very sensible. But it used to be, there was a Badonkadonk tank, which was a personal armored vehicle. There was the T-shirt of the three wolves howling up the moon. There was a gallon of milk, a Tuscan gallon of milk, which was unavailable, but $200. So it was all these things that people had managed to by like buying stuff and fiddling around, and then written fantastic reviews. You know, the reviews are just spectacular. I think this is like down here you'll see someone they're really excited about. This is really good for the right curved bananas, and they hope they make a left curved one. So so there's some really good quality in there. You know, I know you guys. For decades, I've been trying to come up with an ideal way to slice a banana. Use a knife, they say. Well, my parole officer wouldn't allow me to be around knives. Shoot it with a gun. Background check. Hello. I had to resort to carefully attempting to slice those bananas with my bare hands. I would get so frustrated that I would end up squishing it. Anyway, so look at this. So a lot of that sort of stuff. So I have two. Because a student gave it to me at the end of this class, at the end of the semester. Here's a present for you. But and I know we've got to go, but my point is that this is, just let's look at this little thing, and then then you can go. So if you look at their little 5-star review, where's their 5-star thing? If you go to here, so Amazon calculates a product's this is not their average score. It's a star rating based on a machine learned model. So I don't know what this means anymore. Like they discount older ones, they do something funny. So these are, I think if you look at these are real, but then there's a black box that gives you its average rating. Who knows what it means? I don't know what it means. But at least it's got stars and you can order them. All right, I'm sorry for the monologue, and but we'll do it again next Tuesday. So we were at the end of last lecture, I was sort of working through these fundamental pieces. We'll talk about them, I think, for a lot of the rest of this lecture. And then the next piece is robustness. All right, good. Okay, so this general issue of how do we measure things, and of course, ending up with one number being a problem. I'll have some more examples of that. So we got a little bit into this list of examples, and I think it was at this point that the banana got involved. All right, so we had a list of pieces here where we collapse onto this 1D spectrum, 1D line for all these complicated things, because that is easy to compare. So BMI has become one, which is pretty weird, right? I mean, that's taking what is it again? It's like mass divided by height squared or something. What is it? Does anyone know? No one cares. No one cares about BMI. But insurance companies do, and yeah, interesting. I think so. It's a weird. Okay, well, let's look at it. It's a weird one, and dimensionally, it's kind of strange, right? I mean, I'm just super opposed to this thing. Look at that. You can. Thank you. It's like making you do it. It's body mass divided by the square of body height, which is just a weird thing. I mean, if density is somewhat uniform, then and then you have a diagnostic, right? Then you're good or bad. It doesn't matter if you're Arnold Schwarzenegger or something. Yeah, pretty weird. And I mean, maybe it drives some things. IQ, right? So that humanity was quite taken with that for a long time. It's still talked about. It's controversial, but that was you could sort everyone. Certainly, countries used it to sort people in schools for a long time. People got scholarships and all sorts of things based on this thing. There's anyone heard of the Flynn Effect, which is that IQ has been going up and up and up over generations. It's named after a New Zealand researcher who just noticed this, right? And it's kind of a curious thing. And some of the ideas were, it's like, there's much more sort of fiction and people are exposed to a lot more meta stuff, so they're better at there's more school or whatever. But so that was all very good, but it's been going down apparently over the last 20 years. So that's a rough thing. I hadn't looked at it for a while, and I looked it up the other day. I'm like, oof, not great. Effective temperature. This one kind of drives me nuts, right? It's like, it's raining or whatever, and da-da-da, and then it's like, but it's effectively 63 or something. It's just like, we can handle, it tells what the wind is and the humidity. Like just, right. That's just really silly. Of course, money, right? So one dimension, you map everything onto money, right? This thing is worth so much, and this thing, and there's a direct comparison, right? It's pretty good. Salary, right? That's a good one. Stock, so again, this is money, right? So this is what they're worth, yeah. Complexity of civilization, so the link is not working there, but this is Turkin, and this is a paper that just appeared in PNAS, and it's a very, just an enormous effort to get quantification of all sorts of aspects from civilizations across the world over many, many thousands of years to measure some aspect of them. It's like 6 or 7 or 8 aspects that they focus on. And I don't have it written up here, but essentially what they come up with, and they don't really say, they say there's one dimension for, there's a one-dimensional thing for, let me get there, in fact, the right thing. So. Yeah, so historical analysis uncovers a single dimension of complexity. That's it, right? So you're running your country or your city, you feed in all its data and it gives you a number out, and then you're like, we're better than, Santa Fe or whatever, right? Like, yay. So lots of people involved. And it is an interesting thing to have done, but here's the problem in the end, I would say. Right, so there are all these different things. Like, is it a hierarchical? Is it a government measure? Money, money. Like, how developed is it? How developed is infrastructure? Written text. Does it have this sort of thing? Information systems, capital, population, territory, right? And then just population. So these are actually, I guess there's quite a few. There are maybe 9, right? Around the world, and then they do a principal component analysis thing and come up with the fact that there's really this one dominant measure, and actually what it is all of these equally weighted. So you add them all up, right? And there's really not a second principal, like it's really dominated by this first one. So it's basically, you have to have all of these things. So to say then that that's one dimension, I think is not right. And really what this is the Anna Karenina story, right? So the first line of Anna Karenina, it's a little quote, which is, right, that happy families are all the same and unhappy families are all different in their own special ways, right? So dystopias are, manifold, right? There are all sorts of ways for things to go wrong. To keep it all together, you got to have a lot of things operating. And so this is the Jared Diamond story, right, of Guns, Germs, and Steel, was that, and again, actually calling the Anna Karenina principle, that you have to have all of these things before things can take off, right? So you need to have, and this is all debatable and so on, but a domesticable animal and a crop and, water and all these sorts of things. There's obviously some basic things, but minerals, you need to have these things. So, some parts of the world really hard to do that, just, really arid, or you're in the middle of the Pacific, whatever it is, it's just hard to have all of these things running. Okay, so the upshot for me is that, the title is very misleading. It's very misleading. This is actually, you need all of these things to be running, and that's, you wouldn't want to call it a single piece. All right. Last one I have here is, and maybe it's down the bottom. So there's a 1D axis for political ideologies, right? And there are various versions of this that are much more elaborate, but even just 2 dimensions, like a social axis and an economic axis. That's sort of often famously presented. I'm sure BuzzFeed has done that by this point. You can find where you are relative to Gandhi and Stalin and so on. So, but a 1D axis is very, it's just sitting there, and it's the French, I guess, had people sitting on the left and the right, and they eventually just called them the left and the right, and they just became the left and the right. There were just 2 groups, and so it's this spatial metaphor which was just waiting for us to get trapped in, like flies in a web. and it's hard to get out of it. And I don't know what's going on with that now, like as to whether people, I think, may be actually becoming more, there's reality of people's political, like if you ask them the right questions, they turn out to be not entirely on these lines. But there's so much feedback, right, from news and so on, that I think people might be cohering a little more actually on these lines, right? And then it's not even a line, it's just like there's a point here and a point here. So we need to sort of, not get ourselves trapped there. But I don't know, that's a difficult one. So this all connects, I guess, into Facebook and questionable things, but this is work from a while ago. I have a few pieces here measuring personality and so on, and some are jokes, I suppose. But this is a very serious effort based on, I think these were surveys at the time, but pretty large scale. So does this still hold up? Ocean is still considered to be, Matt, is this still considered to be okay for personality? People argue about it.
Oh, yes.
It has a nice acronym.
The Big Five.
The Big Five, right. It's based on these sort of semantic differentials, not neurotic to very neurotic, and then you sort of answer all these questions, and then these are these five. Again, it's a principal component kind of thing. I would presume it was. For meaning, there's valence, which is a happiness, sadness scale, excitement, and a power scale. It's the three dimensions of meaning. But that's work from the 50s, right? For emotion, there's the four of fear, anger, disgust, and sadness, surprise, and happiness. And that's Inside Out, for example, but they left surprise out, which was a surprise. Okay, so these are these five things, and so you start to quantify things. This is, of course, self-reported, and that's a concern. Bigger concern is mass manipulation. This is just measuring aspects of, showing, lots of different systems that we need to worry about, but the big upshot here is not to end with one number. People they really want one number for a lot of systems. Just do not do that. Different things. This is openness, so this is more open, right? For example, in terms of behavior. Could help me. Conscientiousness, I guess not so much. It seems weird, right? New England. Neuroticism, that's us. Yep. Bridging cultures, right? So this is Mississippi and Louisiana. So if you talk about the right things, it's going to work out. Extroversion and agreeableness. So, so nice. Those friendly Vermonters. With our happiness stuff, Vermont is often near the top in terms of the tweets that come out of Vermont. But it's also like closed, like its variance isn't that high, right? So it's a little, things are okay, but it's not as, doesn't get as excited as other places. In terms of most looking around the world, like 24 corpora, 10 different places, Brazil and Mexico, they had the biggest spreads in emotional variance. All 10 languages we've looked at, they all have positive biases, but which is another. It's a Pollyanna principle baked into language. It's really kind of fantastic. Dungeons and Dragons, right? So people figured out they needed some variation in this. It's just kind of funny. Charisma and strength and whatever, dexterity. It's kind of interesting, right? So they make this sort of, we're going to run this game, and you're actually going to have a whole bunch of attributes. It's my favorite show, obviously. But it's from Reddit, and of course, people debate the actual choices in great detail. Right, so there's those. You've got the things, your charisma and all those pieces, and then this is your kind of your alignments, right? There's a law, chaos, and good, evil this way. It's fantastic. My wife is chaotic neutral, I think. Yeah.
Lee is ruining Michael's life. He thinks she's so special, and she's so not. Her personality is like a 3. Her sense of humor is a 2. Her ears are like a 7 and a 4. Add it all up, and what do you get? A 16. And he treats her like she's a perfect 4. It's nuts.
For some reason, this is a thing. Yeah.
Back in Jacksonville, I was in charge of a 60-person dance group. Whenever we auditioned a new dancer, we would rate them in 5 categories: dancing ability, coolness, dopeness, freshness, and smell grade. I would give you an 8 in every category.
This is
8 is the baddest. Oh, no. 8 is the best. It was a scale of 1 to 13, but 8 was highest. The scale went up and then back down, like a 10. Why?
But he gets it. He gets it. Maybe not the 13, but anyway, he gets it. So enjoyable. High quality show. All right. So, so all of that is to say, don't measure things by systems. Whenever someone says, I have some measurement of a system and it's one number, you've got to be very careful with them because they are probably trying to trick you in some way. All right. So, emergence. Let's talk about emergence. So this is a big piece. Yes, there are tarot cards of silliness, but this is the idea, right? I mean, with these little pieces somehow giving rise to larger scales. Of course, hurricanes coming out of water molecules. Thinking somehow comes out of neurons. Pretty weird, right? And then collections of letters give rise to words. So this is some things have changed here. So there's Wikipedia, right? So it actually comes from philosophy originally, which I'll say again, I suppose. Complex system patterns arise out of a multiplicity of relatively simple interactions, right? Remains yet very controversial, very strange. I don't know why. So I got rid of the controversial. This is 10 years later. Where larger entities arise through interactions among smaller or simpler entities, such that larger entities exhibit properties that they do not exhibit. All right, so that's a lot of words there. But this is this rather remarkable thing, right? I mean, I had this piece at the start of the atoms we're made out of, and ultimately quarks and so on. It's not obvious when you have a pile of those things that you could have a human made out of them that does the things we do. So, emergence, and it's usually it's always to do with becoming, right? Somehow something's grown, and how does that come about? So that temporal part is really complicated and difficult. We tend to want to represent things in the start, I suppose, by training some, very complicated things, by training something up, neural networks or whatever, to represent thinking, perhaps. But there's a growth part that we don't always go through. So lose, I guess it was 1875 was when this was first coined. It's really it's a very beautiful word. This is a little thing from.
Fireflies are something that we.
Let me just say, this is Steve Strogatz's voiceover, and it has a lot of good things in it. This is actually David Attenborough floating around, I think, in Southeast Asia looking at fireflies. So Strogatz is Attenborough is Attenborough. Strogatz, we'll come back to him a little bit. There's an Emergence podcast here by Radiolab. This is back when they were incredible. It's season 1, episode 3. But it's a little piece on top, and he has some nice things to say here.
We've all loved as kids, right? Catching them in the backyard, putting them in a jar and watching them glow. So we don't tend to think of them as anything all that mysterious. Well, they do one thing very nicely, which is flash on and off.
That's all fireflies do, flash. But what interests Steve Strogatz, a mathematician at Cornell University, is that there are places in the world,
Not here, but in Southeast Asia, in Malaysia or Thailand,
where fireflies don't just flash randomly like we're used to. They somehow flash together.
there are enormous congregations of fireflies along riverbanks.
How many?
It could be tens of thousands, tree after tree, extending for literally miles along the rivers, all flashing in sync like a Christmas tree, rows and rows of Christmas trees all wired together going off. And it's one of the most hypnotic and spellbinding spectacles in nature, because you have to keep in mind it is absolutely silent. You picture it. There's a riverbank in Thailand in the remote part of the jungle. You're in a canoe, slipping down the river. There's no sound of anything, maybe the occasional, exotic jungle bird or something. And you're looking and you just see whoop, 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 with thousands of lights on
Which one
and then
is
off, all in sync.
Because no one knows.
There are literally 10 theories
What seems to be clear, says Steve, is there is no one firefly that makes it all happen. It just happens on its own. Order materializes out of nothing. And that has him puzzled.
How can order come out of disorder? And this is what the creationists love to talk about. And it's because they don't understand, and neither do we. This is the big mystery of science. I think bigger than black holes or bigger than superstrings. I mean, science has had hundreds of years of success since the time of Galileo and Newton from reductionism, from looking at the smallest parts, whether they're genes or atoms, whatever. That's great. We need to understand the individuals, but that's not enough.
So, right in that last piece, escalates pretty strongly, but it's great. I mean, it's exactly right. So. This is kind of remarkable, right? We see these things, and some we can explain very well. We've done, and I'll come back to it occasionally, and then towards the end of the course, fluid mechanics is an amazing achievement, for example. But all of these pieces, right? They're not, the tornadoes, water molecules, or I guess I should say hurricanes, maybe dollar bills. It's not obvious from any of these things. They don't contain them. That these emergent properties like human emotion would come out of somehow involving carbon atoms. There's this, right? There's sort of this list. I mean, here's your little instruction set, gives rise to organisms, and really fantastic. I mean, we're struggling with all these pieces, but we know the game. We know what we're trying to do now. Thoughts are a very odd thing. I mean, we're still kind of figuring out even which part of the brain does the thinky bits. Right, people do all sorts of stuff. Yes. Gravity is an interesting one too, right? Like, it's just there. We have a very good description of it, but it's just kind of there. Also time, pretty weird. Time is strange. Time is really strange. So, whole is more than the sum of its parts, and in fact, that's Aristotle. There's the I guess I don't have it quite there, but the more is different is the Phil Anderson paper, which is appeared in Science in the 70s and is a really important contribution, at least to science in general. Right, we're saying it's not just particle physics. All of this stuff is fundamental science, because we don't need to know about quarks at this point. Right, there are ways that people interact with each other and so on that doesn't matter about the details. So you have a game that's being played out, and you have to figure out how it works. These are just a touch on a few other areas. So Hayek, and whatever you think of all these things, he was interested in emergent behavior, and of course that's the laissez-faire, I guess, eventually. It doesn't mean that things go well, but you get a lot of where you do get good emergent systems. It's very healthy sorts of things that look after themselves. Taxis means made by God from the top down, grown order, and we need some balance, obviously. But hierarchical and decentralized structures, these are usually good for creating things, right? This is your startups, right? Once you've really solved what you want to do, hierarchy gets put in place. You see that with all sorts of systems, and that's an interesting thing to. Right, there it is. Yeah, once problems are solved, we have some nice work on that, actually, I think. And yeah, this is an old thing, but this idea, this is an imposed system. This out of Dewey's head. I mean, it did get updated eventually. Come to a situation where it gets updated by a group of people. But this idea where you impose this order versus, something like just putting tags on videos or tags on anything, which still exists to some extent. But fine, or even just, extracting from, documents like basic words. Doing something smart. And getting it to tell you what the structure is. That's an old example. This movement away from trying to think about micro behavior, right? So that this is Weber's story was that capitalism arose out of this at this sort of macro level, but this this is Coleman's idea at this point, right? That you get we could talk about it in a micro way. Of course, this is very hard to measure. Potentially, and certainly at the time, it's become more and more available to us. We're in a bit of a funny time where we can measure lots of things about people, like all their little tweets and things, and we can get all sorts of data out about how people use Dropbox or whatever. And we can do that in good and bad ways, of course. So we can be absolutely overwhelmed by the data we have about people, but it's still only this sort of very thin representation. So it's a bit of a dangerous time where we'll find out a lot of things, but then we need more measurements. Shelling. All right, so this is good. I'm going to put this in here. So I've talked a little bit about toy models. I think that's going to be something I'll touch on through this set here, right? So toy models are fantastic things in that they can show us narratives or behaviors of systems that we couldn't intuit. And especially ones that are about collectives and group behavior. We're not very good at understanding that, right? We tend to impose narratives of individuals on lots of things we see. That's easier to understand. We are individuals, something we'll come back to later on. This is so Schelling, who's passed away now, I think. He was a Nobel laureate in economics. And if you want to, these are, I think, well, we've gone across. These are really beautiful books to read, some of these old ones. They're very clear and thoughtful and so on. And he may not be right about everything. But, they're very thoughtful pieces. But he did a lot of, he constructed what I would call, in physics you call them toy models. So model of segregation, right? So this is, a real sort of ongoing issue, of course, but a very specific sort of issue was happening in the 50s. And he was wondering that the general sense of this was that you have two ethnicities, say, and they just don't like each other. Like no one in each group likes anyone in the other group. And so of course they split apart, right? So you see this global behavior of these groups splitting, and then the easy narrative on top of it is that all of the individuals do not like the other group, right? So completely makes sense that this happened. So I'll come back, I'm gonna look at that visualization with you there. So what comes out of this is he started thinking like this. Two different types of coins, put them on a checkerboard, and just laid them down randomly, and then gave them little rules, which was if they have a percentage of people or coins of a different type around them, they would want to move, and they'd move randomly. So it's this really simple little simulation. This is in the 60s. He did some stuff with punch cards, I think, but I think he had one of his kids, and they just messed around with it. So they ran these little simulations. Lots of other things there. So this is if you've heard of tipping point, right? So that neighborhoods were said to tip, and that's where it comes from. The tipping thing. As far as I understand it, was used there, and now we have this tipping point, and Malcolm Gladwell has done bad things talking about it. Okay. So has anyone seen Nikki Case's work in general? Nikki Case, so she's, I should say, they have a pretty fantastic set of things you can play around with here. And a lot of them are, and I've been meaning to talk about them, and this is the right place to start talking about them. There are lots of pieces in here. So this one is something we'll get to later on, which is networks. I'm pretty, they were asking for ideas at some point, and I think I suggested this. So that may be the result of that. This is the one we'll talk about here, but lots of little, really interesting little games that are often about complex system things. So this is polygons, right? So we have blue squares and yellow triangles, and so you can move them around in some cases to make them happy. So this one, so now they'll smile, right? So they'll smile when they're happy. And it's so the game is that you play around with these thresholds. So in this case, they all want to move if they're a third of their neighbors, less than a third are like them. So we'll start to talk about thresholds. This is a very useful word for social phenomena. You have thresholds with respect to all sorts of behaviors. Potentially, there's hard things to measure. At least they make sense theoretically. And once your threshold is exceeded, maybe you start behaving in a certain way. So this one, so I don't know if I can move these ones. Oh, seems sad still. Yeah. Can I move these ones? So you can play around with these things. Let me get this to work. Yeah, okay, good. So there's a new board, so you can just mess around with this and try to get them into places where they're happy. And I guess once they get to a happy place, you can't move them, right? So there is it's not easy to see from the start, like how this will play out. And let's get to a little simulation one. Right, so these ones are, they're going to absolutely, it's an easy thing to do, right? So then you end up with segregation. All right, so here we go. So this is a movement one. The segregation is going up, and it became quite bad, right? So I think that's what that one is. Yeah. So in this case, was it a third in this case? So they have a bias, right? It's just a third, I think, in this case. Right? So I have to remember that. But you end up with global segregation, right? So randomly assigned global segregation. And you don't have them being like, the individuals here aren't that intolerant that this would suggest. They're intolerant to some extent, but not absurdly so. Okay, so here's the threshold, right? So this is the 33%. So you'll move if, let's make it 50%. So even if you want half of the people around you to be like you, it ends up being segregated. It's a really nice little visualization. Even there. So I guess I've said this. So even less than 20%. Of course, this is where you're really, this is the simple narrative, right? Everyone wants to move. Oh no, sorry, less than 100% of the neighbors are like me, yeah. So this one's just messy, right? You're happy with all sorts of things. Stop, sorry. Interesting. So you can get some complicated behaviors. I think down here there is this one. This is the hipster model. We made a hipster model of this, sort of. I mean, it looks like segregation. But if everyone's like you, then you want to go as well, right? So this one keeps going. You don't want everyone to be the same, right? So you want some diversity. I don't know if you can read these things, but that's it's stuff. Okay, so lots of things to play around with there. But, wow. And then so you can change this, right? How many are empty, right? You can play around with all sorts of things. So very nicely done. But the big upshot of this was, as I said, it was a checkerboard to start with, was, this potential way for a macro behavior to come about was revealed. I mean, it was from a little toy simulation. It doesn't mean that's the way things work. We've seen like the rich get richer model from Simon can fit the reality extremely well, and we'll see that again with Ising models, for example, for magnets and some other pieces I'll touch on. They can actually fit quantitative, really get accurate agreement, which is very strange. This is just a story kind of thing, right? This tells you here's a particular dynamical path that can give rise to this macro phenomenon that we more easily, and we couldn't see this story. This is a hard story to see. So again, this is toy models are, and obviously a lot of toy models don't work and whatever, that's fine, but they're super powerful things. So that's the thing you can play around with and learn some more about. Anyway, that's the best version that I've seen. So emergence of taste. I mean, this is a super interesting one, right? So somehow the things we eat and the things we have this whole sense of taste. This is Pollan's article, Nutritionism. Simplest food is hopelessly complex thing to study, right? All these things. And what I want to add here is that we're kind of in that, we're still in this mode of like, here are the constituent elements of a food. We put on the side fats and carbohydrates, whatever. We list them, put the ingredients there, but it doesn't really tell you what it's going to taste like. I mean, there'll maybe some lies about how it will taste. So breaking these things down, of course we have to do this, right? But it does ignore the interactions, but we're maybe building back out to that. I should do the flavor network thing. Yeah, I'll dig that up. Some of the interesting work on recipes, for example, online, which I've pointed to, get at this a little. So it's a reduction of science. That's completely fine, right? But they don't eat. So I guess the big war on fat, right, started from some connections. I believe it was between red meat and heart attacks. And the spin that got put on top of it was the saturated fat, not the meat. And then that became coconut is bad for you. right? And then it became fat is bad for you, and then we ended up with, fat-free, sugar-filled ice cream and stuff like that. And that lasted for a long time, and it really was not good. There's a real fear of fat for a long time. I guess there still is. But, eating fats. It's very animistic, this idea that, that's how you, right? It's not because your body makes things out of sugar or whatever. All right, so it is complex, right? So this is a route that's often taken, right? So that you find something that's good or bad in a food, and then you find the nutrients inside and whatever it is. We need things, vitamins and so on. Beta carotene might increase certain cancers, so you don't want to just go and take all these supplements. Like the multivitamin stuff is really, I think, not great, right? I think there's sort of bad evidence of taking too much of that stuff. This is Times antioxidants, so, it's not what you are thinking about, and which is fair enough. We know it tastes good, it doesn't poison you, right? So it'd be great to know how this works. But meantime, we know it doesn't do any harm. Those people are still around, tastes good. And this is gulf between theory and practice. And to go back to Schelling, we had him come talk years ago at Columbia, and he gave this anecdote about, maybe I've said it better, about how you can't really, maybe we can understand everything about the flow of a fluid around a sphere, a perfect sphere. We can do all the math and all these sorts of things, very difficult, and we can do simulations, but we don't then slowly deform that into a jet. There's not an in-between space there. There's kind of like, let's really solve some hard problems at these very well-defined sort of structures, and then we go right out to the whole thing, and at this point it's like massive amounts of computer simulation. Lots of other examples, like baseball, cricket's the same, like how the balls move. People know, right? Like the Pakistani cricketers discovered reverse swing. No one understood it, but, it was devastating. It's a long time ago. And bumblebees, right? Bumblebees just make no sense. They're too big. And there's a glorious tweet about bumblebees. I should find that one. They're just like back of the envelope sort of things. Like, no, you shouldn't be able to fly. Fluid mechanicist says this is wrong, right? And it took a lot of work to find out, but apparently they make some strange little vortices and so on. There's some very weird little things that happen that make them capable of elevating themselves in clumsy and charming ways. Emergence. So this is my deep analogy between food and the economy, right? So collateralized debt obligation, right? It's lots of things that you probably don't want to eat by themselves or know about, but it looks good, right? And this is the whatever AAA rated bonds, you put them together and it's okay. You put some very dodgy things together and just say, yes, it's great on the outside, and sell them to unsuspecting German investors. I feel like that's an analogy. Anyway, but things go horribly wrong. Looks good, but isn't. All right, just a few more pieces. I will probably finish with this quote from Pratchett. So, right, story's not atoms. Well, it is really made of atoms, but it's a lovely idea. Okay, that's a reference to Supernatural. It's pretty out there. So narrativium, this is great. Most common element on the disk, although not included in the list of the standard 5, earth, fire, air, water, and surprise, which is just basic joking, the element of surprise. But, this idea of earth, fire, air, and water being the constituents of all matter. I mean, that was a good idea. Totally wrong. But, so a little narrativium goes a long way. The simpler the story, the better you understand it. Storytelling is the opposite of reductionism. 26 letters and some rules of grammar are no story at all. And lots of fantastic places of emergence and so on, but we'll talk some more about it on Thursday. You have this problem set, which is based on Mandelbrot's work, so which we talked about last week. So I'm kind of putting this in here as get some more general happiness in here. Well, I shouldn't say that. General story for the whole course in here, and then we'll get on to robustness. I might start that actually on Thursday, because it's quite fantastic. Okay, liberation. Thank you. office hours now. Yeah, that's good. All right, I'll talk about that some other time. Okay, so good. I'm going to add a few more pieces here about fundamentals. I want to make sure I don't, I want to get into talking a little bit about percolation at least. Right, okay, for sure. So this is Gödel, who was one of our famous people who weren't doing so well. I think he thought everyone was poisoning him, right? Yeah, it wasn't good. He was a bit worried about stuff. So, and it's just sitting around here. It's true. We can't prove every theorem that's true. Right? This is a weird, super weird thing. It took a really weird analysis to get there. But, you know, given a set of axioms, right? This is your rule set. Given a set of axioms, you can have a different one that gets you the same truths and so on. So this is from Gödel, Escher, Bach. This is this idea of things we can prove, right? That we can kind of, and there's no, actually, Andy Regan did some work on this. Like, you know, what's the network of theorems and stuff look like if you have a well-curated kind of field? You know, what's it look like? You build out from your axioms, and then you build all these pieces on top. These are negations of theorems, right? So, or something is, you know, the other way. So going by a falsehood thing, and then there's the stuff we can't prove in the middle. So that's a really weird phenomenon. This is just sort of to add to, you know, what we're talking about with emergence. This is a strong idea of emergence, which is really magic, of course. So I'm not really going to go on about this too much, but sometimes you'll see this framing. Weak emergence, which is something that we have this system level phenomenon, this macroscopic behavior that's clearly not, you know, obvious in any of the individual parts, but we can get there theoretically, whether it's simulations perhaps or equations or whatever it is, right? And then there's this kind of notion, and this is coming from more philosophy, right, that there's no way you can actually derive it. But certainly people are worried about this in terms of the brain, right? So it just could be to make a brain that functions like a brain, we have to make a brain. Like we can't really, you know, make a sort of you know, we've certainly created neural networks to do all sorts of things inspired by, but to, you know, replicate one of these things, which runs on 20 watts. Or something, right? It's pretty ridiculous. Like we think Watson's pretty smart, but you know, like it's not much, 20, 30 watts with a few wrinkles. Okay, so magic would explain strong emergence. So it's a little bit of a, we don't need to worry about this too much. Okay, right. Yeah, so maybe of course, you know, when we're imputing magic or some sort of ethereal power to why things are the way they are, then perhaps we just haven't got there. And that should be our experience of where we are now, right? So science has had this tremendous success over the last couple of hundred years. Less threats by people to get rid of you if you have bad ideas. I think, let me see if I can come back to this one. This is about, so it's about 12 minutes long. I want to play this towards the end if I have sufficient capacity to do that. This is a fantastic, you know, I've got these old Radiolabs that I've really enjoyed. So this one was called Limits. It's from now 8 years ago, and it moves through from physical limits of humans to intellectual ones, right? And this is from the intellectual part. It's just a large threatening animal outside. So it's just what you guess, right? So the first stuff is actually about Ironman triathletes crawling across lines, which is probably not a great idea for them. And then I think this guy was a Slovenian army guy who won right across America 5 times in a row. And that's a game where, you know, where people about 10 days into that can become completely lost mentally, right? So he would get off his bike and try to fight things like mailboxes. And, you know, you're just gone. They're like 3 or 4 hours sleeping. So they're really hallucinating and so on. And apparently with that guy, he would say things like the Russians are coming through the trees like military. And they would say, yes, they are. They would use that as to help him ride faster. Anyway, so it goes through this. There's the memory, the very famous, is that real? The M, I think it was called, the Russian character who could remember everything. I think some of it's not quite true, but there was this fellow who basically could, and he had all this synesthesia going on. He'd be watching all this stuff happening, and he would add all these colors and swirls and whatever, and he could basically play back a videotape of his experience, and became a show. He'd go to a big hall. So there's a Russian guy who'd go to a big hall and have people just shout out things for 10 minutes, and they'd be able to repeat it all. Apparently read Dante's in Italian and could recite, but that's not entirely true, I think. But it is weird. It's only not many pounds of stuff running on not much wattage. That for some people they actually can remember everything because they do not seem to have the capacity to erase things, right? So a healthy brain actually, you need to be able to forget stuff, or especially as you're sorting out just even meaning, right? Not just about good or bad things, but just making meaning of things. You can't just keep a huge list of everything that's happened. You have to start to make sense of it. Anyway, that's in this. It's a fantastic piece. And then I'll come back to it because at the end it's talking about the limits of science. Okay, let me see if I can remind myself to do that. Interesting. This will require concentration. That's good. I guess put a little timer, right? So what is it now? 40 minutes. Okay. All right. All right, so self-organization is a term you might hear. I'm just going to mention a couple of other terms that are floating around. And so this is the idea that there's no control, right? There's no control system somehow, and famous examples, flocking and mobs and so on. Protein folding has this. There's nothing telling it what to happen. I'll have some examples of magnetization. Right, so, lots of examples. That's just a term. How likely is complexification? So this is a really wonderful, spectacular question, right? And I think we understand, like a piece that I've just added, at least for myself recently, is that the formation of stars is an inevitable thing once you get a universe. So that's a big piece. The origin of life remains this open problem. Thinking about society, how it goes up and up and up, but can collapse, right? Very important. All right, so this is just to say, it's kind of fun, this is as I said, this is kind of a bit of an odd collection of things. So there isn't, one set of tools that tells you you're in complex systems or whatever, but it's basically all of the modern things of science, right? So differential equations, I realize, work more for continuum things, but they're still obviously very important. We need lots of things for descriptions these days. There's a lot of statistical techniques, lots of models that are stochastic in some way. There are really fundamental pieces coming from StatMech, and we'll show some of those in a little bit. Oh, and the black box issues of machine learning. So there's a great lure right now that we can seemingly do everything, but we can't understand. Of course, we can't understand anything, and so a lot of people don't really care about that, right? So anyway, so computer modeling, and I've talked about this gap between these sort of toy models that are well-defined and easy to understand, but have really interesting behaviors and tell you things that you certainly couldn't intuit just by thinking. You have to simulate them. And then everything, you model everything. All right. We'll have this soon. This was the gigantic, I think this was really, the big change was getting enough data about systems, to be honest. Many kinds of systems, but eventually getting enough, and involving people, right? Systems that involve people. That was got a lot more people excited. And the thing is, there are networks under many of these systems, and that opened up tremendous amount of work of all kinds, really. But the driver is data. All right. Okay, so this is a fun little piece here. There's a whole interview which you could watch. But this is where you want to get to with the science. This is going to seem ridiculous, but this was published in Science magazine. There was one of the authors is at, maybe both of them are at MIT, and one of them was watching his cat lapping milk one morning, right? So, and thought that was pretty interesting because the cat was sort of like making the milk sit up in the air and then going chomp. So cats and dogs have different lapping. Dogs just sort of like slap it and try to get it up in the air. It's a little more straightforward. But cats do this weird thing where they poke it and then it makes a little pylon like this and they go chomp. So he thought this was interesting. He's a fluid mechanics guy. And the thing is, so what this escalates into, which is total madness, they made a little robot out of something that was supposed to be on the space station that could, like, you know, do this. So they make a physical simulation. They get all the theoretical stuff to work, and they can do, you know, simulations within a computer and get it all to work. And they ended up with figuring out what the frequency. So there's a scaling here for the frequency of lapping as a function of size of cat. Here it is. So this is really important, right? So this is mass to the minus of 6. And here it is. There's a nice scaling. So they have different organisms. So cat, tiger, ocelot, lion, because they went onto YouTube and found videos of large cats that actually do this in situ. Here's their little robot. Now, why am I showing this? Because it's really a bit silly. But the thing is, they get the three pieces together, and this is a mature science can do this, right? They're able to do prediction and everything that you want, but it's because you have, you know, real data, you have a model, which you can, experimental model, and so on. So, and then a theoretical piece. So and it's fine that we're not there with everything, right? We just sort of have to step back sometimes and reflect on where we are. And so when there's not enough data, or like no data, then theories are abundant, or, you know, they explode really, because nothing's being constrained. You know it's important. And then when data comes along, well, it's a battle for a while, right? We don't really know what we'll end up with in terms of models for a lot of, say, social phenomena. Maybe we won't. Okay. So this is going to be about StatMech and a couple other pieces. So, you know, every time I look around to see if someone's got a better, like, little online model thing that's doing a good job, but I wasn't really sure if I found one for percolation. But let's talk about this a little bit. So StatMech, statistical mechanics. So it's an oxymoron, right? It's very weird. This is something that was created at the end of the 1800s, I think the term comes into being. But it's this idea that instead of, you know, we're thinking about all the atoms in this room, there's this sense from the mechanical age, and certainly the great success of all of these theories of mechanical machines and so on, that, well, what you'd really want, right, is the exact path of this little molecule, and it hits this one and bounces off, and it's like a huge thing of billiards, really hard, right? That's kind of what people were used to thinking about doing. So that's obviously impossible, right? Too many things. And then this notion of statistical mechanics. We'll do things kind of on average. We'll imagine, you know, roughly how things are working and give them distributions and so on, right? And that was, I mean, looking back to that Einstein 1905 paper, was that's, you know, this cornerstone in us getting to knowing atoms exist, understanding atoms exist as the Gaussian distributions, random walks, talked about these things. Okay, so statistical mechanics. So, right, it shouldn't, how can you have probabilistic mechanical systems? Well, you absolutely can. So, in the way we model them. Chaos is a different thing. Okay, so percolation. So this is a really simple idea. So and you could really easily simulate this for yourself, right? You just make a matrix in whatever, you know, code or software system you use, and then just with a coin go to each one and weighted coin, right? So with probability P, you make it white, and probably 1 minus P, you make it black. And then the idea is that these white ones are kind of like open pores. This is like closed-in material. You can think of it like that. And then the question is, can you, if you start over here and you want to run through to the other side, right? Can you do it? So in this case, no, right? There's no connected way of getting through here. You're not allowed to hop. You imagine this is like a little cave structure or something. And the notion is percolation, right? Which percolating through the ground. There's also coffee, which made, you know, scientists happy to talk about this, right? But the idea is, you know, can material, can a liquid flow through this? So there's a toy model for that sort of problem. So a lot of the motivation for this came from oil companies originally, I think, was sort of, they got excited about this because they wanted to get things out of the ground. I guess eventually I gave up and just went to fracking, just blow it up. Fracking makes this happen, right? So this is where we've dialed P up, if you like, and this probability of, and they're all uncorrelated, right? There's no connection from pore to pore in terms of whether it's open or closed. You just flip a coin at each time. So this is a case where, yeah, you can walk through it. So obviously for P equals 0, it's all dark. There's no way you can get through it. For P equals 1, this is all open, so you can walk straight through it. So what happens in between, and what does the structure look like? If you think about this, lift this off and think about this as being a network, and you start to think of these people being, they're infected or not infected, or you can think about edges as well, right? So it's really the connection between them being open or not. So you could flip the coins on each of these things. Is there a doorway here or not, right? And then of course you can have different lattices. And then you might think this is a universality problem. Well, maybe the details don't matter, right? That would be a nice, you don't know what's going to happen, but that would be a nice kind of thing, right? We love that sort of stuff. It doesn't matter if it's hexagonal or like some other funny kind of lattice that maybe isn't regular. But it turns out it does matter. So that's, let me show you that. Don't think I have a simulation for it. Yeah, nope. Yeah, so percolation threshold. So the percolation threshold, that's the value of P for which you just start to get a connected component that allows you to walk from one side to the other. We'll have various terms for that, but giant component is often used, or the giant cluster, a percolating component, right? So you can see there's a list of these things, lots of different kinds of grids, lots of different values, right? So these are site percolation and bond percolation. So that's the links. This is the door thing, right? Whether you put a door at the side of each square, and site, whether you're allowed to go through it or not. So in a sense, all the doors are open around a site. It's just whether you can go through it. And so they have different values, and you can see people have worked out all sorts of madness to like ridiculous numbers of decimal places and got really carried away. So that's great. But the thing is, there isn't a universal piece here. That really depends in detail. We'll come to this later on in the course, because towards the end when I talk about some other universal pieces. But macroscopically, if you simulate things on grids, then you can see that grid at a large scale, depending on what your simulation is, but you can kind of see it, right? If you simulate things on hexagonal lattices, then you can't see the hexagonal lattice. If it's a big enough thing and you step far enough away from it, you can't see that grain. There's no grain of a hexagonal lattice. And in fact, if you make a hexagonal lattice and kind of squeeze it like this, do stress and strain, it feels like a solid. There isn't a sort of, but if you get one of these together, you can do this and you say, oh yeah, there's some weird thing there's some microstructure in here that's not, that doesn't appear to be like a continuous solid. That's something for later on, but hexagonal things are pretty spectacular. All right, so this is a simple thing to play around with. What else do I have here? So easy to simulate. The one tricky piece for this is, for example, so let's say we come to this one and we want to count up all the connected components. Sometimes these things are built into whatever you're using, MATLAB or Python. You could find someone's made a package of it, but it's not a bad problem to think about for yourself, right? So you'd start here. This isn't part of an open pore, so you just give up, and you kind of march across and you find this one is open, and you say you've visited all these, and then you look at all its neighbors and see that it's closed, and so you'd mark this as kind of group 1. You could do that. And then go across, you mark this as group 2, it's not connected to anything else. And then maybe when you get to here, this is group, whatever it is, 7 or 8, you just put a 7 here. This is already visited, so this is a 7, 7, 7, 7. So this is, you'd see this, right? You could do something like this. And then you'd have all these labeled groups and with sizes, and then you could plot a histogram of them. And what happens is, before you get a giant connected component, you kind of have the sharp decay in size. But just as you get to this point between these two cases where there's a percolating component and there's not one, as you get to which is the critical point or the percolating threshold, you get a power law size distribution of, yes, you do, power law size distribution of these little blocks. Just on that cusp, right? So we'll come back to this for robustness. That got a lot of people excited. This is called the critical point. This is, right, it's the same sort of thing with ice forming. You kind of get these bigger, lots of little pieces, some number of smaller pieces that are a bit bigger than that, and so on, so on, and so on, and then a big piece, and eventually it makes one big giant component. So that's fun. And then so the idea is that, oh, maybe lots of real systems with these power law size distribution things, they're somehow like this, but they're being forced back to this threshold. Something in the world is making them go to that threshold. people get very excited about. They call it the edge of chaos, or the term that popped up was self-organized criticality, and we'll come back to that later on. But the idea was, again, this word self-organization, there's nothing dictating it, there's no big lever that's pushing it, from outside that's pushing it this way into this percolating point, or this critical point, percolating threshold, but somehow it comes about. And I don't know, there are there's a lot of debate about that, but we'll see what we talk about here. All right, so this is a different thing. This comes out of the 30s, and it was just a PhD student, I believe, Ising. In Germany, just came up with this ridiculous model for magnets, right? So this is a joke magnet. It's a toy model, and let's try it and see what happens, right? So you've got, and they could be all sorts of things, right? So this is upspin and downspin. So that's the idea. We want to see if our magnet goes this way or that way, or has nothing going on at all. And we're going to make, in this case, it's a 1D one. And then we can have a grid version. You can have all sorts of things. You can have a 3D version if you want. Just each point on the lattice has a little tiny magnet itself, right? So this is a bit of a, I guess, a MIMO, magnet in, magnet out situation. So that's cheating a bit. But we do know that these little characters have spins, right? Homunculus. It's the homunculus approach, right? Okay, right. Magnets inside magnets. All right, so that's the idea, though. There's a little local spin, and you can just add them all up, right? And so you'll see from this is a beautifully developed world of theory and models and so on, and then eventually computers came along and tremendous excitement. People say, well, what if this was voting, right? What if this is voting? So there are lots of parallel things that are inspired by the Ising model. It's a kernel of a great amount of development. These people are neighbors. They could be on a network. They see their friends voting or whatever, and yeah. So, and some of that stuff is just it's not really right to do some of it. They get a little carried away. But anyway, this is the kind of thing you see. So there's an overall temperature that this thing is bathed in, and that's making these things jump up and down potentially, right? So if it's really really high temperature, then they're being affected. There's a lot of thermal sort of noise that's pushing these things. They're just jumping around, and they can't really care too much about their neighbors, right? But as you lower the temperature, there's a natural coupling, right? Like magnets like to line up with each other, so there's a natural coupling that comes about, and so they start, and depending on how you connect them up, so it's all just sort of four neighbors. So in this case, this one here is not happy, right? Because its two neighbors are pointing the opposite way. This one is, this is okay, this is a bad one, this is a bad one, this is a bad one. So this is a frustrated one, if you like. And you can have all sorts of things where, they can or can't move, and you talk about spin glasses and frustrated systems and so on. All right, so what happens with these, and again, it matters, the grid matters to some extent and so on, but as you lower the temperature and you have your little model here, then eventually they can get connected enough with each other or care enough about each other, right? There are these sort of two things pushing them, and there'll be one side which will be favored. And so the macroscopic magnetism of this system will go in one direction, either pointing up or pointing down, because the ups win or the downs win a little bit. And let's see if I can run a little simulation of that. But this, it depends where you start, right? So you could start here and then heat it up, and then by this point it's all just static. As you cool it down, it could go to here. This is maybe an initial point at a particular temperature. It would quickly go to this point, right? So you started with it being maybe completely messed up, it would jump. So this is a phase transition story. Very important thing for systems. It's a phase transition, right? These are really different phases. This is like, gas and water. They're different things. You can have hotter and hotter gas and colder water. Eventually you hit another threshold, but they are of the same phase. So there is a real transition point there. And often in these systems, it will depend on, as you hit here, there's going to be some growth away from this. How sudden is this, right? It could be a sort of a smooth thing, or it could be disjoint. We talk about, how explosive those points are. Okay, so the Drosophila, right? It's the fruit fly of stat mech. Everyone loves the Ising model. Right, power law size distributions at the critical point. Now, of course, it's just this one point, so that's a kind of a knock against it being accessible. So here's a little example. I think I can just, so it's all messed up. It's got, let's make the temperature kind of high. So this is just going to bubble, right? That they're trying to, they would like to be the same as their neighbors, these little magnets, but the temperature is pushing them around. And so as soon as you drop the temperature down enough, then they start to coalesce, and you'll see like, right, this is going to get eaten up, went away, and that's going to happen. This will, because it's on the edges, right, because it's rounded a little bit, on average you're going to be exposed a little bit more to people who aren't like you, right? And so you will, ooh, it has a weird hand. And peninsulas are dangerous, right? This is not going to work out. That one's going to get, it's going to be dangerous at the end. It's going to eat back onto it. Chomp, chomp, chomp. There was a paper in Science a few years ago that claimed that this was a thing that leads to instabilities in regions for countries, right? So if you have a peninsula of a country going to something else, then that's a bad thing, right? And I don't know if that held up, but you know, it's definitely an appealing thing. It's like, okay, right? Sort of makes sense. Anyway, so that will get eaten up, and of course, as you you can just destroy it again. You get to the critical temperature, which is 2.2? Sort of hold apart, yeah, and then it's gone. So you can see this is a very simple model. There is this big outside thing, this temperature, right? There is one big piece from outside. It's true that everyone experiences. And that could be, so you can see how people are going to take this in all sorts of directions, like voting. There's some temperature, some ambient background kind of disposition of your state or your country or whatever it is, and you have some randomness on top. So local plus global. All right, that's good. Gosh, you can do all sorts of things with this. Yep. Okay, craziness. Ooh, let's make it bigger. That's harder. All right. Right. But it is, right, it is, you can see this will take a long time for itself to kind of, for all of those things to fight. It started as even, right, 50-50 basically. Once it's all random, it's 50-50. So coming back, depending how quickly you pull the temperature down, it's going to take a while for this thing to sort itself out. All right. Okay, that's a thing. So a couple more pieces to put in here. But generally speaking, for systems, you know, this is a great achievement if you can get to having a so-called phase diagram. So this is for fluids, for liquids, right? This is an incredible achievement. But it's something we really like to get to, right? Qualitatively distinct macro states, liquids are different than gases, different to solids again. But we're moving around in micro details, right? We change the temperature a little bit and so on, but we're still a gas. So that's this nice kind of universal aspect there. There are various examples. This is a really crazy one from a few years ago now. So there are famous old experiments of shaking water and getting out all sorts of patterns, and they're often hexagonal and so on. So this was just an update of that with granular media. So these are just tiny little ball bearings just shaking on a speaker. And it turned out you could get these localized things. So really quite different to what happened in fluids, although maybe some people achieved them. They called them oscillons, ended up on the front cover of Nature. You know, just a different behavior. And this is fluids have all this universality. When you get to granular media, which is super important, right? It's all around us on the Earth and all our foods and so on. We have lots of granular things. It's fluid-ish, but not quite, right? There are some weird behaviors with granular media, like silos, for example, right? So silos, when you fill them up with grains, the stress. So if it was just water, then it would the pressure would just increase on the bottom, right? It would be just very simple. There'd be forces on the side. But silos, you get these force chains in granular media that can go sideways, and silos sort of famously sort of split open sometimes because you've got weird structures. Very dangerous things too if you get underneath grain and you get a cavity come down, and then it's all stuck, right? But a little dislodging, and yeah, bad things can happen. So they can, and so sometimes, depending on if you're like moving, rice from one box to another or something like that, sometimes things get stuck, right? And it's not just humidity, but something, and you just have to shake it, and then it all comes out in a big, Anyway, that was a fun thing. So they have phase diagrams here, right? Same idea, like which frequency and amplitude you get these little oscillons. These are all things. This is life, right? So this is different shapes we're getting out of growing bacteria as a function of wetness and how much nutrient is being provided. Snowflakes do all sorts of things. Traffic, we have different things based on density of cars and so on. Right, so just a general thing for phase diagrams, hard to get to. Okay, this is an important piece. It's just reality. So if we go back to the Ising model, so it was the 20s. This was solved in 1D, and that's something you can work on at least for percolation. 1D, simple to solve, you can do it. Pretty much always, it's not interesting. You can solve it, nothing really surprising comes out of it. 2D, very hard. It was eventually solved mathematically, at least for this one square lattice by Onsager. This is a very famous work. And then 3D is just ridiculously hard, right? It's just crazy. And you can simulate it, but simulation even becomes hard at 3 dimensions. So it's just a lot that you need. So this is sort of solvable, not really solvable. And then for a lot of things, though, once you get to 4-dimensional versions and higher, or maybe, they become simple because they've got so many they begin to have so many connections that it becomes it becomes possible to make it like a so-called mean field thing where you're connected to everyone, something like that. So this is just something I want you to sort of know about systems in terms of the dimensions they live in, that high dimensional spaces can be actually the systems can behave in pretty nice ways. And we just tend to live in this world. So that's a bit unfortunate for us. And then one extra piece to add this, we'll get to networks. Networks have really everything in them, right? So the local dimension, a node has so many friends. That's kind of like a local degree. And so you end up with a very mixed kind of space, which is weird. This is just a nice little thing. So StatMech, the inspiration for StatMech was based on the study of people, because this is sort of one of the first places where, like actuarial type things, people were figuring out how many people got kicked to death by a donkey last year and then saying that's a good prediction and so on. And people were a bit upset about that because it's kind of weird, right? Just to be able to estimate roughly, and worried about fate and so on. But that was where and people were using kind of probabilistic things. And so then it turned the other way around, right? So StatMech became let's use an Ising model to explain the United States voting. That's not right. So that's critical mass. All right, so once we get out of, so StatMech's had all this success, but of course there is an algorithmic aspect to them, but really once you get into evolution and biology, and then of course our information systems and social interactions, there's a lot more algorithmic stuff. So this is just a where are we going? Where are we going? All right. Game theory is a good example there. So a little nutshell, complexity and emergence, these are good things, right? There's no general theory of complex systems. You don't have one model that does it. Universality means that we can, and I know I've sort of said this earlier, but universality means that you can actually really have some hope of doing something that will apply across many fields potentially, or at least many kinds of situations. And that's just reality. That's not anything we've imposed on top. Right? It could have been that the equations that we have for honey are different to the ones for water in really giant ways, but they aren't. All right, describe and explain. All right, that's good. So there's a lot of extra pieces there. Let me just think about this. Don't quite want to show this. So I will show this other. Let's go back to this. Nope. Okay, so we're going to go back to, and I may have to click on it. Why don't you do this? So weird. Okay. I think the best way will be to click on it. Hopefully it's all.
Hey, I'm Jad Abumrad.
I'm Robert Krulwich.
This is Radiolab, and this next segment began with a simple question.
Seeing as our topic so far has been limits, and we've done body,
And we did the brain.
now we're going to go really big.
Yeah.
Yeah, so we called up Steve Strogatz, mathematician at Cornell University, frequent guest on the show, and we asked him.
Are there limits to human knowledge?
Yeah. And his answer sent us on a little adventure.
Is there anything that's at the limits of our knowledge is a question that a lot of us scientists worry about. And certainly the 20th century taught us that there are many things that limit our knowledge. For instance, the Heisenberg uncertainty principle in quantum physics showed us that you can't know the position and momentum of a subatomic particle at the same time. You just can't do it. It's not a matter of not having good enough instruments or not being clever enough. It's just a fundamental barrier that nature puts in your way. In logic, Gödel's theorem tells us you can't prove certain things even though they're true. So there are all kinds of limits, but those seem a bit remote from everyday experience. And yet, I think there are really important limits on our knowledge that we're all familiar with. What I'm thinking of here is our inability to think about big numbers. Because with your fingers, you've got 10, normally. So we're good at 10. We're barely good at 100. And once you start getting to thousands, millions, billions, and trillions, it gets hazier and hazier. When you hear now about the trillions of dollars in the deficit, or whatever it is, the debt, that means nothing. How are you supposed to think about that? Now, when you ask, why can't we understand the common cold, but we can put a person on the moon? It has to do with large numbers.
Not just large numbers of numbers, says Steve, but large numbers of things interacting.
That there are so many genes involved and so many biochemical reactions involved. Our brains are limited. Our memories are very limited. And so I worry a little bit that we might be approaching the end of our ability to have insight into certain kinds of questions.
What Steve means by the word insight is not like he found the answer. It's like that.
It's like a feeling.
Right.
Like that, oh, I get it.
The feeling you get when you really understand the answer.
Yeah, that satisfying feeling that I can see the reasoning.
I can actually feel it in my bones.
That's a very pleasurable feeling, but one that we may not always be able to enjoy.
I mean, you can see the space. Good luck.
We weren't really quite sure how to feel about this,
Right.
but then Steve said, yeah, don't take my word for it. Talk to these guys that work down the hall for me. You'll see.
Yeah, we can go right ahead.
Cool. Can you guys introduce yourself? Tell me who I'm talking to?
Yeah, so my name is Hod Lipson.
My name is Michael Schmidt. I'm a PhD student.
And I'm a roboticist.
And Hod and Mike have developed this thing, which does make you wonder if Steve's right. It's a computer.
Yes.
Actually, many.
A whole tower of computers that are all grinding away and performing calculations.
Actually, when you get down to it, it's just a piece of software, but they've named it.
Eureka.
Because that's what it was designed to do, to have eureka moments.
Maybe a kind of simpler example.
And the story of Eureka begins pretty simply, with a
regular pendulum, okay?
With a pendulum.
Just one of these things you see hanging off a grandfather clock.
Okay, I've got a regular pendulum swinging in my mind.
Okay, swinging left and right.
Now, says Hod, double it. Instead of a string connected to a ball, make it a string connected to a ball, connected to another string, connected to another ball.
Which is basically like a double pendulum. The cool thing about this is you just put it up, you lift it up and let it go.
And what you'll get, says Mike, is
chaos. This really crazy behavior.
Instead of nice and even, now you got random.
It's almost impossible to actually try to predict where this thing will move.
So what they did was they got a camera, connected it to Eureka, and basically just had Eureka watch this thing, move about crazily. And then they asked the computer a really simple question. Can you make some kind of sense out of this erratic behavior? Like, is there something in this system that always stays the same?
Tell me, what about these pendulums over time is not changing?
Because with everything, there's got to be some kind of logic in there. So you're looking for a law, basically. I mean, you're looking for the law of the double pendulum.
Yes, that's the idea.
So Eureka is there watching this pendulum.
It was about 3 a.m. in the lab.
And it's basically spitting out all of these different guesses.
It's formulating hypotheses.
It's getting closer. Closer.
And then onto the screen pops this simple formula. F equals ma. What is F equals ma? Is that actually the law that...
F equals ma is Newton's law of motion.
The Isaac Newton.
That's Sir Isaac to you.
It's a basic law of physics.
And one of the greatest discoveries in the history of human thinking.
Took it about a day, 24 hours. But the interesting thing is that it came up with this thing without knowing anything about physics, nothing. That's why we think that this algorithm might be able to find new laws that we don't know about yet.
In fact, once word got out about Eureka,
that's when the emails started.
A couple of emails a day.
From scientists all over the place who were like, hey,
you mind if we borrow your robot?
For what kinds of stuff?
Anything you can think of, from trying to predict behaviors of cows in a herd, to particle physics, to the stock market.
And this is when we get to Steve's point about the limits of insight.
That's when they met this guy.
My name is Gurul Soel.
Gurul is a biologist.
At the University of Texas Southwestern Medical Center.
He got in touch with Hod.
And he said, I have this amazing data, which is single-cell dynamics.
Meaning he's got this tiny little thing.
It's a simple bacteria.
Really basic.
And he's been collecting this information on how it works.
On its inside.
How things go up and down. Certain nutrients increase, certain nutrients decrease over time, just like a pendulum.
But the thing is, in a cell, it's like thousands of pendulums.
There's so many parts.
Genes turning on and off.
Thousands and thousands, tens of thousands.
Proteins turning on other genes, nutrients going up and down.
It's this crazy quilt of complicated feedback.
And he wanted to know, inside of this cell, how are all of these things related? I mean, we can measure it all, we can see things going up and down and all that.
But what are the rules?
What are the rules?
Yeah.
And this, he says, is the problem for biology.
Biology is one of the least well understood systems compared to, let's say, chemistry and physics.
They're still lacking the basics.
So we said, look, Mr. Robot, can you tell us what you think are sort of the important principles governing this organism, and maybe detect things that were hidden from us?
So he sent us the data, and we analyzed it. And
well, okay, let's not. Yeah. So what happened?
Suddenly, equations started popping out.
Almost immediately.
The robot came back to us and said, okay, here's a set of 2 equations that describe your data.
Do you remember by any chance what the actual equation was? Not that we'd understand it, but just sort of to hear it said out loud?
Yeah, no, I don't. I don't have my Rain Man skills developed to that degree yet.
The important thing is that the equation was telling him things like, when this protein goes up, this other thing always goes down. And when that thing goes down, this gene turns on, and then there's a loop-de-loop. And when he went to his cell to check all this out, the equation was right.
These equations match the data. And in fact, they explain new data.
These equations could even predict what the cell was about to do. But, hold the champagne, there's just one little problem here. The formulas check out, but...
we don't know what they mean.
You don't know what they mean.
Right.
Meaning they don't know why these equations work.
Why when this goes up, does that go down? Why when that goes up, does this go sideways? Why?
I had to first look at this and try to make sense of it. We said like, oh, okay, I think we understand. And we're like, oh, maybe we don't. We think that we're close to understanding it.
But, now we're in this bizarre situation. We can't even publish it right now because we can't just publish a equation without explaining it.
So in the end, they're in this awkward position where they've got the answer, but they don't have the insight.
And I think it's a preview of what's to come in science.
The more we turn to computers with these big questions, the more they'll give us answers that we just don't understand.
We'll be faced with this challenge of having to find ways to get a computer to explain what it found.
But that will leave us, if this really happens, in some weird position as bystanders where we're sort of listening to the oracle, but not really understanding the answer. Is there going to be a time when we can't cut it anymore? We've had this this window in human history when we could not just know things, but actually understand them. That is, you could know why they were true, not just know, but to know why. And that's a beautiful moment in human history, but I feel like it may only be a moment.
Well, I don't really see it quite that sort of sad and dramatic, because at the end there will be simple principles to describe even the most complicated of processes.
So you have a bias that prevents you from feeling the kind of despair that Steve feels and that we were hoping you would feel.
Oh well, I have a positive outlook.
Well, I'm just wondering about the we. Look what we have discovered, you'll say when you're an old man with your robot sitting there in a dress next to you. And the robot will be holding your hand, but that will be a cold hand. And Jad and I will be thinking, I don't know, who's the we here?
Well, I would say we is sort of knowledge. I'm just thirsty for understanding and thirsty for knowledge. Me and the cold hand holding my hand, we've accumulated and contributed to the overall understanding of something that we thought maybe 50 years ago wasn't possible. And that would be something that would make me happy.
Right. Okay. This is very interesting. I think it holds up. This is deep learning was only just starting up, right? That was only just starting to gain some traction. So that was, but this work was done really around the same time. Josh Bongard, who's here, was part of this group. So they said they were roboticists, and so Hod Lipson, he did his postdoc with Hod Lipson at Cornell. Nick Cheney, who's just come back, he was an undergrad here, and now he has a research position here. He was a PhD student with Hod Lipson, who's a very famous character. So I don't know if that paper was ever published, but I think they've had other things like that too, which they can predict stuff, but it's very unsettling because they have equations. It's different to having a deep learning thing that predicts stuff, but you're not even trying to understand it, right? That's some sort of game, fair enough. This is something where there's something that you should be able to understand potentially in front of you. So, very interesting piece. I don't know, and maybe Strogatz is not far off. We don't know. I don't think there will be simple explanations for certain things. All right. And the slow TV thing, that's just there for therapy. There's plenty of good stuff around. That's from Norway. I think they just they had this thing where they just hooked a camera up to the front of one of their trains and put it on basically PBS. They have one for a ferry that goes for 4 days. Just a ferry. And I think it might have started off with just video of wood burning, people making fires in the woods and burning it all. And that's just on TV, right? Very enjoyable.